Hey guys, this is Mr. Krieger. Today we're going to be doing AP exam review number 4, review of confidence intervals. So you should print up the lesson. Okay, so review of confidence intervals. We're going to go over how to construct them, identify the parameters, check the conditions, perform the calculations, and interpret the results. This is important, and you could read this yourself. Don't use the language of probability for confidence intervals. What you're going to say when you conclude a confidence interval, when you write a conclusion, you are going to always say, we are 95% confident that the true whatever, average or proportion, I used a particular example from our class, the average grade on the AP statistics exam for Mr. Math's AP statistics class is between 3.05 and 3.85. It's very important that that's how you write a conclusion for confidence intervals, okay? So we're going to try a problem. Okay, confidence intervals for mean when the population standard deviation is known. Now remember that that is not something that's usually known. You don't. That's a rarity, but it could happen on an AP exam. So let's take a look at let's take a look at a situation. We've done this problem before, but it'll be a good review. A study of the career paths of hotel managers were sent questionnaires to an SRS of hotels belonging to major U.S. hotel chains. There were 114 responses. The average time these 114 general managers had spent at their current company was 11.78 years. Construct and interpret a 99% confidence level for the mean number of years general managers of major chain hotels have spent with their current company. And here they're giving us the standard deviation for the population. Again, that's not normally something that you would know, but let's just say it is. Let's say it's 3.2 years. So this 11.78, that's X bar. This is not the true mean. It's the average from a sample. Hopefully that sample average is close to the true average for all general managers at major U.S. hotel chains. But this is just a sample average, so it may or may not be truly representative of the true mean mu. All right? So I worked out this problem ahead of time so that we could save a little time. So again, like I said, we don't know sigma. We know sigma here, so that's not usual. But because we know sigma, we would use a z interval. That's the type of confidence interval we're going to be using here. Let's check the conditions. There's always 3 conditions that need to be checked. First of all, was it a simple random sample, SRS? It was stated over right here. It was an SRS, so you'd say stated in the problem. Now normality, that can be checked in a variety of ways. First thing you should check is to see if the central limit theorem applies. Since the sample size was 114, the central limit theorem does apply. So you would say that the sampling distribution is approximately normal. Nothing is truly normal, but it's normal enough for us to use this confidence interval technique. Okay, independence. You need to make sure, and you have to check it, like numerically check it, that the true size of the population is at least 10 times as large as the sample. There were 114 people in the sample list, so there has to be 1,114 general managers to ensure that independence is assured. Okay, we're saying we're using a z interval. Okay, and what you would do on your calculator is you would go to, let's go over here, we're going to go to tests, and it's z interval number 7, and we have statistics here, we don't have data, and let's put in the information that they gave us. They told us that sigma was 3.2. They told us that x was x bar is 11.78, and there was 114 responses, so that's our n value, and we want to do a 99% confidence interval. We're going to change that to 99, and there are our numbers. I wrote them down over here. Write down the key statistics. Write down what your x bar is. Write down what your sigma is. Write down what n is. always state that state that what you're using. We're using the z interval here. You can write down the interval, and then you need to carefully say we are. Accidentally put down 95%, but in this case it's a 99% confidence interval. We're 99% confident that the true population value of the number of years that a hotel manager was with their current company is in the interval 11.008 years and 12.552 years. Okay, so that was the first question. Okay, let's take a look at the bottom here. Confidence intervals for means when the population standard deviation is not known. So if you don't know sigma, in other words, you have to use a standard deviation from the data, you just use a t-interval. So it's pretty easy. Remember, for the t-interval, you do need to know degrees of freedom. You could write that down. Degrees of freedom is always the sample size minus 1. A couple of things. Except in the case of small samples, the assumptions that the data comes from an SRS of the population is the most important assumption. Okay, so that's really important. For the population, for normality, of course CLT is always going to apply, but T procedures are robust. So if you have a sample size that's less than 15, just make sure that take a look at a box plot and make sure that it's relatively symmetric and that there are no outliers, okay? Otherwise, don't use. If it's at least 15, just make sure there's no strong skewness. When you take a look at the next problem that we're going to do, just make sure your box plot is pretty symmetrical. And of course, for large samples, you could always use T procedures because of the central limit theorem. So let's try the next problem. Okay, I'm going to have to put this data in now. I had it in originally. Okay, so here's what we have. We have computers in some vehicles calculate various quantities related to performance. One of these is fuel efficiency or gas mileage, usually expressed as miles per gallon. For one vehicle equipped in this way, the miles per gallon was recorded each time the gas tank was filled and the computer was then reset. Here are the miles per gallon values for a random sample, so there's our SRS of 20 of these records, so 15.8 miles per gallon, etc. Okay? Is it appropriate to use the confidence interval with the T procedures? So here I worked this out. By the way, I'm not going to re-enter this data because I had done it already, but if you go into your stat, if you go into, let's stat edit, you can type the data right into L1, and then we're using a T interval, so when you go to stat test, make sure you choose T interval, okay? All right, so let's talk about if the data was normal. Well, first of all, SRS, we already knew that was the case. It was stated in the problem. Normality. To go to the box plot, you would put your data in, then you would go to second stat plot, make sure you turn the plot on, go to, when it comes to the type of graph, go to this choice that shows the outliers, and your data should be in L1. Then if you do zoom 9, you'll get your box plot. So I actually made a sketch of the box plot. You can see it's a little left skewed. No outliers, but because it's a T procedure, the T procedure is robust and there are no outliers. It's not necessarily truly normal, but the sampling distribution is approximately normal, so we could use the T interval. Independence. Again, it has to do with there being at least 10 times the amount of things in the population as there were in the sample. So we had a sample size of 20. It's reasonable to assume that you could get 200 records of miles per gallon. Okay, so here it asks us to construct a 95% confidence interval for mu. So we're going to use the T interval because sigma is not known. The standard deviation, you get that straight from the calculator. It will come up when you run the interval. Don't forget to put down the degrees of freedom. Degrees of freedom is going to always be n minus 1. So the degrees of freedom is 19. So for T intervals, you need that degrees of freedom. And here's the interval that they gave us. So it's between about 17 miles per gallon and almost 20 miles per gallon. So you could say, and this is how you're going to write it. This is really so important that you get the language down correctly. We are 95% confident that the true average gas mileage for this vehicle is in the interval 17.002 miles per gallon, and 19.938 miles per gallon. Okay? So this is the situation where you don't know the population standard deviation. Okay, let's go take a look at the next thing. Paired T procedures. Okay, so what's important here is to know that there's two ways to get data that's comparing things. One way is to compare whole populations to whole populations. If you're doing that, if you're given the population, the Chinese GDP versus American GDP, and you just got those whole population values, those aren't linked up one-to-one. That's comparing a whole mean to a whole mean. But what if, like I'll show you an example here, individual data are paired up? In that case, it's called a paired t-test, okay? That's going to be a paired t-test. So you're going to make the differences in the values. So you would literally subtract these values. We'll take a look at this example in a minute. Okay, and you would, again, just use a regular t-interval. This is how a t-interval is written. We're going to use the calculator to get it. Let's actually take a look at this example. Okay, so a researcher conducted a study to investigate whether local car dealers tend to charge women more than men for the same car model. Using information from the county tax collector's records, the researcher randomly selected one man and one woman from among everyone who had purchased the same model of an identically equipped car from the same dealer. The process was repeated for a total of 8 randomly selected car models, and the purchase price is the difference between woman and man, and it's shown in the table below. So this car model was bought by a woman and a man. The woman paid $20,100, the man paid $19,580. For this model number 2, a woman paid $17,400 and the man paid $17,500. In this case, the man paid more. Well, what you need to do is you need to literally take the differences. So I actually showed that here. For car model 1, woman minus men was 520. The woman paid $520 more. For car model 2, the woman paid $100 less. For car model 3, the woman paid $900 more, and etc. And that's the data you're working with right here. You would enter this data into your calculator. In fact, I'm going to do this one. I might have the data in there. Let me see if I do. No, I don't. I'm going to enter that data so you can see what we need to do. 520, negative 100, 900, 200, negative 10, 1200, 1300, and 670. Okay, so now I got my data in the calculator. Let me just double check it. 13, 12, negative 10, 200, 900, negative. Yes, perfect. All right. We got to check the conditions. SRS, it was actually stated in the problem. If you go back and read the problem, you'll see it's there. Normality. Let me show you how you get this, because I want you to show you, really, for such a small sample size, if it doesn't say the data was normally distributed, then you're going to have to check a box plot. So how do we do that? Go into second y equals, which is the plots. Make sure this one is on, the one that shows you, the box plot that shows you outliers. Okay, we're getting our data from L1. Now, if you go to Zoom 9, it's going to show you the box plot. And you see what I did? I actually copied down, I made a sketch of it, so approximately how it should look. Maybe I didn't do a great job, but try your best, okay? The box plot is symmetrical, and since the T procedure is robust, we can assume that the data is approximately normal. That's good enough, even for a small data set, in order for us to go ahead with the T procedure. Okay, independence. It's reasonable that this procedure can be repeated 80 times, that we can get 80 pieces of data the same kind of way. We're doing a paired t-test, so we're going to be using, I'm sorry, not a paired t-test, we're doing a paired t-interval. So it's basically doing a t-interval. There's nothing really special about it, except you have to create the data by taking the differences. Once you go into a t-interval, you would, and I'm actually going to show you how to do it here, if you go to stat tests and we want to do a t-interval. So let's go down, that's the 8th choice. We're not doing statistics, we're doing data. The data is coming from L1. The only other information you need to include is what is the confidence level? In our particular problem, the confidence level, it said, was 95%. So we're just going to have to change this value to 0.95 and calculate, and it's going to give us that interval, which is 141.31 and 1028.7. Write down all this information here. X bar is 585. This is the standard deviation we use for the t. It's the sample standard deviation. We do not have the population standard deviation. That's usually what happens. N is 8, and we should write down the degrees of freedom, which is easy because it's 8 minus 1, it's 7. We have our confidence interval. Basically, women are paying more, between $141 and $1,028 more. We are going to say this is how you write it every time, we are 95% confident that the woman spent between $141.31 and $1,028.70 more than men on the selected car models at this car dealership. Okay, so that's how you do a paired t-test. Okay, confidence intervals for proportions. Okay, now there's one proportion intervals and two proportion intervals, but no matter which kind of interval you're doing, proportions are always going to be z. You don't have to worry about t or anything. It's always got to be z. Now, the one thing you have to look out for when you're doing a z interval is that normality is checked differently. Everything else is checked the same, but normality, it's n times p hat and n times 1 minus p hat. Those values have to be 10 or more. Other than that, it's really the same kind of procedure. Let's take a look at an example. You want to see how many students at your school have allergies. You take a random sample of 80 students and find that 23 have allergies. Calculate and interpret a 95% confidence interval for the true proportion of students who have allergies. So I've worked that out here. Okay. Confidence intervals for proportions. Again, like I said, always use z. Here's the p hat. We actually take the data that we knew. We had a sample of 80 people, and 23 of them had allergies, which is a p hat value of 0.2875. Notice, we don't know what the true proportion of people at this school have. We don't know the true proportion that have allergies. We only know from this particular sample, it's about 29%. Is that reflective of the true proportion? Maybe. If we make an interval, we should be able to capture that true proportion, okay? We got to check the conditions. That's always kind of the same, except for the normality. SRS, check, make sure it's stated in the problem, and it is. Here, for normality, I wrote here, got to show your work. Not only do you say n times p is greater than or equal to 10, sure, you write that down, but then you show the calculation. N is 80, p is 0.2875, that equals 23, and that's greater than 10, yes. N times 1 minus p is 80 times 0.7125. That's the difference of 1 and this number. That's 57. That's greater than 10. So normality is okay. Independence. The school has to have at least 800 students in it because your sample had 80, and you need to make sure that there's at least 800 at the school. So you could say it's reasonable to assume that there are 800 students at the school, or there needs to be 800 students at the school in order to use this interval. Then let's go take a look at how to do this. When you go to your stat, here we're doing a one proportion z interval. One prop z interval. You have to go down a little bit. One prop z interval. Let's see what we got. X was 23. There were 23 allergy sufferers, and N is 80. And we wanted, was it 95%? 95% confidence interval, so calculate it. So I'll write down these numbers, 0.188, etc. It's right here, 0.18832 and 0.38668, which means about between 19% and 39% of the students suffer from allergies. But this value that we got, 28%, that's a guesstimate, but you're most likely to capture the true percentage of allergy sufferers inside this interval. And then you write correctly. You're always going to write the same kind of thing. We are 95% confident that the true proportion of allergy sufferers at this school, it's particular to this school, is in the interval 0.18832 and 0.38668. All right? So that's how you do a one proportion z interval. Now, I didn't do a two proportion z in this lesson. If you feel you want me to do it, just email me. I can do an example for you. I just figured, we did that more recently, and if you feel like you need extra practice, let me know. Okay, the last thing we're going to see and we're going to do here is determining the sample size in order to make sure our margin of error is an indicated value. In other words, suppose I want my margin of error, let's say talk about the allergy sufferers. That margin of error that we had there, I'm going to go back to that last problem and bring it back. Take a look. This is a big interval. It goes from about 19% to 39%. So that's 30 percentage points difference. No, I'm sorry, that's not right. That's 20 difference. So the margin of error is about 0.1, approximately 0.1. Suppose I don't want such a wide interval. Suppose I want it to be 0.05. I'm going to have to take a larger sample. So 80 is not going to cut it. I might have to take a sample of 200 or 300 or 500 or whatever. So if I want to make that proportion narrower, I'm going to have to choose a larger sample size. But how do I figure out what my sample size should be? That's going to be what we look at right here. All right, let me just put this underneath here. Okay, so the goal for the user of statistics is not only to have high confidence, but also to have a small margin of error. You want your confidence interval to be narrow. And you can do this by taking a large enough sample, okay? So the margin of error, if you remember, I'm going to rewrite this thing here. Z star, this is the margin of error, times, I'll just put sigma over square root of n. That's the margin of error. Now, x bar plus or minus this gives us our confidence interval. But we're not interested in the whole confidence interval. We're only interested in this thing, which is the margin of error. We want it to be less than or equal to a specific value. Let's do an example. This example we've done in class, but let's take a look at this again, okay? Researchers would like to estimate the mean cholesterol level of a particular variety of monkey that is often used in lab experiments. They would like their estimate to be within 1 milligram per deciliter of blood. They want the M to be less than or equal to just one, it's not point, it's 1 milligram. Okay, 1 basically, right? That's what we want. So we're going to have to take Z star times sigma, or it could be S, over the square root of n, and it has to be less than 1. So whatever we want our margin of error to be equal to or less than, we put it here. Okay, so now the next thing is, there's other things that we should be able to know. The one thing we don't know is n. Let's take a look at more of the information that they're given, and let's see where to put it. They would like the estimate to be within 1 milligram. That's our margin of error. We want to do a 95% confidence level. Now, you could always look that up, but we know that a 95% confidence level is 1.96. If you wanted to check on your calculator how to get that, you could always go, and this is, again, a refresher for you. If you go to your distributions and do inverse norm, and we want our area to be, we want a 95% confidence interval, so we could do 0.975. Think about why that would be. And you could do 0 and 1 there, and you get 1.96. Remember, it's 0.975 when you put it in here, because 0.025 is here, and 0.025 is here, 95% is here, but if you add the 95 and the 0.025, it gets you 97.5% of 0.975, and that's going to give you that z value. So that z value is 1.96. Now they're giving us the sigma is 5, and n is what we want to figure out in order to make sure that our margin of error is less than 1. So what you're going to do here is let's divide both sides by 1.96. And that's going to be, this side, this cancels out. You get 5 over the square root of n is less than or equal to, is about 0.5102. Cross multiply again. I'm going to move this up here. You get 5 is less than or equal to 0.5102 rad n. Divide by 0.5102 on both sides. And you're going to get a radical n on this side. And on this side, you're going to get 9.8. I want to get rid of this square root, so I square both sides. And I get that n has to be greater than or equal to 96.04. So I need 96.04 monkeys, but I can't get this part of a monkey. I'm not going to round down. I got to round up to the next one. You could fool around you could fool around with these numbers by yourself. If you run this confidence interval, if you use 96, you're going to see your margin of error is going to be bigger than 1. But if you use 97, your margin of error is going to be less than 1. This is the number of monkeys you would need to have in order to guarantee that your margin of error is 1. Okay, your homework is the last 4 pages of this document, and that will be due Tuesday.